Digital trust is no longer just about certificates. We also need proof that data stayed intact, evidence of when it existed, and confidence that a transaction is legally recognized. That is where KSI and eIDAS come together, connecting technical evidence with regulated trust. You already have the PKI foundation: keys, certificates, authorities, signatures, and trust chains. Now we broaden the question. Instead of focusing only on who is trusted, KSI helps answer whether data existed at a specific time and whether it changed. That prepares us for comparing different trust anchoring approaches, including blockchain. PKI is a foundation for digital trust, but it is not the whole architecture. It helps prove identity, authenticate parties, encrypt communications, and validate signatures tied to trusted private keys. Still, other questions remain. Has a record changed? Can we prove it existed at a specific time? Will that proof be accepted in a legal or regulatory process? Complementary mechanisms address those gaps. KSI provides scalable integrity and time evidence. eIDAS provides legal recognition and rules for trust services. Together, they broaden trust from identity alone to durable, verifiable, and recognized evidence. KSI starts with a simple move: turn data into a cryptographic fingerprint. The fingerprint is fixed length but highly sensitive. Change one character in the original and the hash changes dramatically. KSI signs or anchors that hash, not the data itself. This keeps the content private and avoids copying large records into the trust system. Later, verification repeats the same hash calculation and checks it against the KSI evidence. If it matches, you can prove the data existed then and has not been altered. The claim is integrity, not personal identity. Aggregation is what lets KSI handle scale without weakening proof. Each record, log entry, sensor reading, or transaction is reduced to its own hash. Those hashes are combined in pairs, then combined again, until one root hash represents the whole batch. That root is what gets committed and anchored. Later, verifying one item does not require the entire dataset. You only need that item's hash and a short proof path back to the root. This makes integrity verification practical for massive, fast-moving systems. Keyless in KSI does not mean there is no cryptography. It means the proof does not depend on every signer protecting a private key for every object. In traditional signatures, if a key is compromised, expires, or must be revoked, trust in related signatures can become complicated. KSI shifts that dependency. Objects are hashed, the hashes are aggregated into compact proofs, and the result is anchored to time and published. Trust comes from verifiable hash evidence and infrastructure, reducing long-term private key risk while remaining cryptographically strong. Time-based proof answers a precise question. Did this data exist by this moment? The data is hashed, creating a fingerprint that reveals nothing about the original content. Many fingerprints are aggregated into a single root hash. That root is then anchored to a trusted time reference, such as a public log, blockchain, or time authority. Later, a verifier can recompute the data hash and check its path to the published anchor. If the path and rules validate, the proof shows the data existed no later than that timestamp. That is why the timestamp becomes useful evidence. Verification is where KSI becomes useful as evidence. A verifier starts with the record being tested and recalculates its hash. That result must match the hash represented in the stored KSI proof. Then the verifier follows the aggregation path, checking each link to prove the record was included in the larger structure. Finally, the proof is compared with a trusted published anchor. If the path reaches that anchor, the verifier can confirm both integrity and time. The key point is independence. Anyone can repeat this check without trusting the original system. KSI is strongest when the question is, has this data changed and can we prove when it existed? That makes it a good fit for audit logs, system events, supply chains, registries, medical records, and forensic evidence. Its value is scale, privacy, and verification that lasts without relying only on private signing keys. But KSI is not an identity or authorization system. By itself, it will not prove who approved an action or whether they were allowed to. For that, pair it with PKI, identity, access control, and legal trust services. eIDAS is the EU's rulebook for making digital trust legally meaningful. It defines assurance levels, trust service provider roles, and categories such as electronic signatures, seals, timestamps, delivery services, and certificates. The key idea is connection. Technical controls gain legal recognition. When a service meets qualified requirements, parties can rely on it across EU member states with far less uncertainty. That matters because digital transactions often cross borders. eIDAS gives organizations a common language for identity, authenticity, integrity, and legal effect in the European digital market. Think of trust services as the infrastructure behind legally reliable digital transactions. A trust service provider may issue certificates, create timestamps, support electronic signatures and seals, or validate them. When that provider becomes qualified, the bar is higher. It must satisfy eIDAS requirements, pass audits, maintain strong security controls, and remain under supervision. The result is not just a technical service, but a legally recognized trust service. Relying parties can check trusted lists to confirm qualification, then accept the transaction with far more confidence across the EU. Under eIDAS, not every digital approval carries the same weight. An electronic signature is the broad starting point, any electronic data showing intent to sign. An advanced electronic signature adds assurance. It must be linked to a specific signer, identify that person, and make later changes detectable. A qualified electronic signature goes further. It uses a qualified certificate and a qualified signature creation device under regulated trust service rules. That is why its value is legal, not merely technical. In the EU, it is generally treated like a handwritten signature. Electronic seals solve a different problem from electronic signatures. A signature links a document to a person. A seal links it to an organization, such as a company, ministry, or public authority. This matters when documents are generated by systems rather than manually signed by an employee. For example, an invoice or certificate can be sealed, so the recipient can verify two things. It really came from that organization, and it has not been altered. Qualified seals add stronger assurance because they are issued under eIDAS qualified rules. The key distinction here is between proving something technically and having it recognized legally. A KSI-style timestamp can provide strong evidence that particular data existed at a specific time and has not changed since. That is technical assurance. Under eIDAS, a qualified electronic timestamp adds a different layer. It is issued by a supervised qualified trust service provider and receives defined legal effect. So KSI evidence may be powerful, but it is not automatically qualified. In real systems, both layers are often combined to satisfy engineers, auditors, and courts. To wrap up, PKI gives us identity, authentication, certificates, and signatures. KSI extends trust with hash-based integrity, aggregation, keyless proof, and time-based evidence. eIDAS adds the legal framework for trusted electronic transactions. The key lesson is that technical assurance and legal recognition support each other, but they are not the same. Next, we examine blockchain as another trust anchoring layer.